Hi everyone. Well, today we are starting the lecture on energy management systems. And my name is Stanislav Yaroshenko. I'm from Power Engineering Institute of Federal University. And the contents of today's lecture will cover the energy management systems concepts with some details on reasons for power system dispatch control. We will talk about different types of energy management systems, and mainly we'll focus on data flows and data processing in EMS systems. Then we'll talk about some peculiar features of organizing energy management systems for photovoltaic power plants and consider the examples of EMS systems for PV power plants and actually what are the data issues dealing with implementation of this energy management system. Well, let's start then. One of the earliest applications of online centralized control actually was to provide a central facility to operate economically several power generation plants, supplying the loads of the system. Modern integrated systems have different types of power generation plants, like coal-fired thermal power plants, hydro plants, nuclear plants, oil and natural gas units, etc. The capital investment, operation, and maintenance costs are different for different types of power plants. Central Dispatch Control Center, the core of the power system generation, dispatching, and network control, is the center of the national electricity supply operations or the region electricity supply operations. The tasks of the Dispatch Control Center are to operate the national power generation and the transmission grid of the whole country, including water resources coordination, thermal and nuclear power plants dispatching, and high voltage substation and network control. The operations in Dispatch Control Center are on duty 24 hours a day and 7 days a week to monitor the system operation state, meet the power demands, and maintain the stability and security of the power system. This actually how the big nationwide power system is controlled, and it's absolutely evident that such kind of a power system cannot be controlled without application of modern, up-to-date energy management systems which cover all the automated issues of control, monitoring, service, maintenance, whatever. Now let's talk about different power system states and some peculiar features of power system operation, because it provides a more detailed understanding of what actually are the requirements imposed for energy management systems and Scada systems as well. So let's start. In the normal operation state, typically all operation constraints of the power system are satisfied, indicating that generation is adequate to supply the existing total load demand and that no equipment is being overloaded or damaged for some reason. In these states, power generation reserve margins are sufficient to provide an adequate level of security with respect to stresses to which the system may be subjected, like short circuit current, I don't know, like weather conditions, extreme weather conditions, whatever. If the security level falls below some threshold of adequacy, or if the probability of the disturbance increases in some circumstances, then the system enters the alert state. In this state, all constraints will still be satisfied but existing reserve margins would be such that some disturbance could result in a violation of some constraints. For example, equipment would be overloaded more or less severely above its rated capabilities. In insecure alert state, preventive actions can be taken to restore the system to the normal state back. If a sufficiently severe disturbance takes place before such preventing action can be taken, the system enters the emergency state. Here, inequality constraints are violated and system security will have been breached since the security level would be below zero and practically non-existent. The system, however, would still be intact, and emergency control action could be initiated in order to restore the system to at least the alert state. If these measures are not taken in time or are ineffective, and if the initiating disturbance or a subsequent one is severe enough to overstress the system then starts to disintegrate, and it's like in some of the extreme state. In this state, equality as well as inequality constraints are typically violated. So the system would no longer be intact, and major portions of the system load would be lost. Emergency control actions should be directed towards salvaging as many pieces of the system as possible from total collapse. Well, once the total collapse had been halted, if there were any remaining equipment operating within rated capability, or some equipment have been restarted following total collapse, the system could enter some sort of the restoration state, which with control action being taken to pick up all lost loads and reconnect the system. From this state, the system could transit to either the alert or to the normal state, depending on the circumstances. Actually, this flowchart describes the transition of different states of the power system. And in the majority of cases, emergency states of a power system are coped together by the automation, emergency automation, and relay protection, and by the actions of the engineering staff, power system dispatch control centers engineers. And within the framework of providing manual control action, the dispatch control staff have to take weighted decisions of what should be done to restore the system and enter the alert or back to normal operation state. Without energy management systems, without adequate data visualization and information provision, the dispatch control staff will never be possible to adequately control the power system state. The electric power system is undergoing dramatic transformations. Actually, you've learned about it a lot within the framework of multiple video lectures within the framework of our summer school. And well, it's worth noting that emergence of renewable energy sources, they reflect these transformations. However, integrating these resources into the electric grid has proven to be difficult for two main reasons. These resources are uncertain and distributed. When the power system increases in size, the number of substations, transformers, switchgear, and so on, so their operation and interaction become more complicated. So it becomes essential to monitor this information simultaneously for the total system, which is called energy control center. So it's just like the building, the control room, where the power dispatch controls engineering staff provides monitoring and control of the power system state. A fundamental design feature of the dispatch control center or like energy center is that it increases system reliability and economic feasibility. In other words, energy management is performed at control center called system control center, covering all of the possible issues dealing with conventional technologies like thermal power plants, network management, operation, maintenance, whatever, and including new energy sources which are distributed, storage, small-scale generation, renewable energy sources, and other active components of the power system. A power transmission and distribution system is that portion of the power system that moves power from where it's produced to where it's consumed. Well, basically, it is the entire power system sans generators. The transmission and distribution system interconnects all the disparate parts of the power system and thus to a great extent determines the character of the system. Beginning in the late 20th century and continuing into the 21st century, significant changes, advances, if perhaps not true breakthroughs, began to occur in several of the technologies that made up electric power systems. It became possible to build electric power systems fed by many more but individual smaller generation sites. No longer would there be thousands of times fewer generation stations than energy consumers. Conceivably, the ratio could be 1 to 1. Such distributed power systems, in which power production is dispersed widely throughout the energy consumer base rather than concentrated at a few generation stations, as in a traditional power system, had different reliability, maintainability, and operability characteristics, as well as different economies of scale, which shaped their use differently from traditional power systems. Neither type of system, traditional or distribution, um, is necessarily better. They are merely different. What seems clear is that the power system of the future will be neither one, but instead of a hybrid mix of the both, the effective interaction of transmission network and distribution network comprising multiple distributed generation sources and active participating consumers. An energy management system is a system of computer-aided tools used by operators of electric utility grids to monitor, control, and optimize the performance of the generation or transmission system. Although it can be used in small-scale systems like microgrids, what is really important that there are many different types of EMS systems, and these systems are of crucial importance not just for big power systems, but for transmission and distribution of electrical energy, for consumers, for other parties like even united generators. So these systems are implemented at each level, and for this reason it means that at each level these systems solve various tasks. The computer technology is referred to as Scada EMS or EMS Scada, and in these respects, the terminology EMS excludes the monitoring and control functions, but more specifically refers to the collective suite of power network applications and to the generation control and scheduling applications, both for generators and consumers. Now let's talk about SCADA. Well, actually, SCADA is an acronym for Supervisory Control and Data Acquisition. Supervisory control and data acquisition systems are used to monitor and control a plant or equipment in industries such as telecommunications, water management, waste control, energy, whatever. A typical SCADA systems comprise signal hardware, controllers, software, networks, and communications. Supervisory control and data acquisition system is a system in which message or commands that are individual are sent to the external world. Well, it provides a host control functions for the supervisor to control and define settings of equipment or system in general. When talking about SCADA concept, it worth noting some basic functions and technical requirements imposed for these very specific systems in order to be able to implement them for power system monitoring and control. Well, the first point, which is worth noting, is data acquisition, converting, and processing. First of all, the systems you need to monitor, I mean the power systems, are much more complex than just one machine with one output like capacity or electric current. So it means that a real-life SCADA system needs to monitor hundreds or thousands of sensors. Some sensors measure inputs into the system, for example, water flowing into a reservoir for hydropower plants. Some sensors measure outputs like voltage, current, power system frequency. Some of those sensors measure simple events that can be detected by a straightforward on-off switch called a discrete input or digital input. In real life, discrete inputs are used to measure simple states like whether equipment is on or off, or tripwire alarms like a power failure at a critical facility. From the point of view of the power system, a discrete input could be referred to the state of the circuit breaker, like it's switched on or switched off, which is very useful to monitor the topology, the configuration of the power system in general. Some sensors measure more complex situations where exact measurement is important, like power flow, energy output, solar irradiation, whatever. So these are also analog sensors which can detect continuous changes in a voltage or a current input, for instance. Analog sensors are used to track voltage levels, temperature, and other factors that can be measured in a continuous range of input. For most analog factors, there is a normal range defined by a bottom and a top level. Actually, you can use these margins, these constraints, when making filtration of the data set because it's very important to have the data set clear. The next important feature is data communication. In real life, you want to be able to monitor multiple systems from a central location, like a central dispatch control center, providing monitoring of the state of the operation mode of all of the power system facilities within the framework of the control zone. Well, that actually means that you need a communication networks to transport all the data collected from your sensors. Early SCADA networks communicated over radio, modem, or dedicated serial lines. Today, the trend is to put SCADA data on Ethernet and IP. For security reasons, SCADA data should be kept unclosed within the framework of local or wide area networks without exposing sensitive data to the open internet. And well, the last but maybe not the least of important points is data presentation. A real SCADA system reports to human operators over a specialized computer that is variously called a master station, a human-machine interface, or a human-computer interface. The SCADA master station has several different functions. The master continuously monitors all sensors and alerts the operator when there is an alarm, that is, when a control factor is operating outside what was defined for a normal operation state. The master presents a comprehensive view of the entire management system and presents more detail in response to user requests. The master also performs data processing on information gathered from sensors. It maintains report logs and summarizes historical trends. An advanced SCADA meter can add a great deal of intelligence and automation on your system management, making your job much easier and making your solutions more justified. The human-machine interface is an integral part of the system that operators use to interact with SCADA, while the larger SCADA system does the work of collecting and storing SCADA data and controlling equipment. Human-machine interfaces typically feature screens and ideally user-friendly dashboards and controls. They may use graphics and visualization to make data and features easier to use and to understand. A human-machine interface is an essential element of a SCADA system since it's what you use to interact with and manage the system, control the system. Without a human-machine interface, you could not take advantage of many useful features of SCADA. The SCADA system, on the other hand, provides the actual functionality. Human-machine interfaces and SCADA are often referenced together because they are a part of a very big and complex system. Just imagine the data flow, the big data flow, when we acquire and collect data from various sensors and monitoring systems. So it's absolutely obvious that the dispatcher, the engineering staff controlling this zone of the power system will never be able to process and interpret all the data that we have from all of the sensors and systems. For this reason, automated data processing, automated data generalization and visualization is of great demand for adequate and effective control of the power system. An energy management system is usually a collection of computer-aided tools used by operators of electric facilities to monitor, control, and optimize the performance of the generators or transmission, or distribution system. Different computer-aided tools are implemented from short time control modules to scheduling or commitment of power production units on a day-week basis. EMS has the objective of maximizing system performance by monitoring and control functions which require a centralized system of data collection and decision-making procedure. EMS are automation systems that collect energy measurement data from the field and make it available to the users through graphics, online monitoring tools, energy quality analyzers, thus enabling the management of energy resources. So EMS capabilities include monitoring and control of the complete power system, validation of data, monitoring power system operation mode indicators, sending control commands, and communication with power industry facilities, display of measured and computing data, operating the system within the framework of the limits, tracking some energy balance, and like even restoration of the power system after emergency. Well, as I have already mentioned, energy management systems are of crucial importance not just for the power system control in emergency mode or normal operation modes, but for separate and individual power system facilities. For example, photovoltaic power plants. They are of great importance for transmission and distribution system operators, for owners of power system facilities. And in this slide, you may see the output, yes, the result on how the energy management system for photovoltaic power plant may look like when we check the states of all of the consistent elements of PV power plant, like production, battery storage, controlling the load, and controlling the grid connection, where we may see that the power transmission line is disconnected due to the fault. If we deal with various control objects and elements within the framework of the energy management systems of the PV power plant, we may see that these are the PV panels, inverter and main control room, which controls the states of the semiconductor equipment, the weather monitoring stations, which provide us with the very important information on the weather events, weather conditions, which actually affect the operation mode of the photovoltaic power plant as well. Um, as I have already told, data preprocessing and visualization is of great importance for energy management systems because it is not a great deal to present raw data to a person who is responsible for controlling the operation state, who is responsible for taking decisions which have impact on the energy production, ensuring reliability and safety on power supply. And actually, that means that adequate preprocessing and user-friendly visualization of these data flows is of crucial importance for all of the existing energy management systems. Data preprocessing is no less important than building mathematical models. Moreover, data processing is an integral part of EMS systems. In many cases, this stage is most important for the successful solution of the problem under consideration. So whatever the problem could be, like forecasting, control of the state, putting some controls and commands, whatever. So data preparation can be divided into the following stages. It's data selection, cleaning, transformation, analysis, and visualization, as well as feature engineering, which stands mostly for machine learning. Generally, the process of data preparation is iterative, and there is no strict order to follow. So we can start with visualizing raw data, and based on the visualization, we can immediately discard something, then clean the data from noise, errors, outliers, apply any additional transformations, and analyze and visualize the results again. So finally, we can come up with the new vision. So after which we understand that we need additional data and maybe some other data sources. And at this stage, we may return to the very beginning and start data preparation for our EMS system again. Anyway, in order to reduce the number of iterations and not to go in blind, we first need to understand the problem from the point of view of the application area. So it's very important because union of the competences either from the application area or from the fields of IT and information systems is of crucial importance in order to build an integral, well-justified and useful system for the problem under consideration. Actually, we have to think about, so what is this problem about? One could be the criterion of the solution quality. And you need to understand if like selecting this very specific mathematics or this very specific filtration function is worth it all. Only then you determine what data to be collected from different data sources. Well, now let's consider the basic operations used in energy management systems for cleaning the data used by the system to provide the corresponding functions to the engineering staff. Since data can be from different sources, we can get duplicates. We can get multiple records about the same objects, which is not really appropriate because it will distort statistics of the parameters under consideration. Some of the data may be irrelevant. For example, we may consider diagnostics of a certain type of power equipment, but in the initial data in the reports, we also have some data about another type. Or, for example, we are dealing with photovoltaic power plants forecasting, and we are basing our forecast on the wind speed, so it's inappropriate as well. We need to clarify, understand that the data we are working with is what we actually expect, yes, and we have to clearly understand what kind of data we discard. This also includes detection and elimination of erroneous records as well. In addition to erroneous records, which may result from faulty measurement equipment, they may be errors in the data structure. For example, differences in physical quantities units using different text designations for the same concept class. For example, from the point of view of photovoltaic power plants forecasting and implementing energy measurement system for it. Well, let's think, what is the difference between partly sunny and partly cloudy weather? So it's rather, arguable. Yeah, and for this reason, um, we have to keep the straight line and to find out what exact cleaning data approaches we are going to implement. A separate stage is outliers processing. Outlier is an object from the data sample which is statistically very strongly out of it. The problem with outliers is that, on the one hand, outliers can greatly reduce the quality of the models of the system because some algorithms are very sensitive to outliers. And on the other hand, sometimes you cannot simply discard outliers because they may not be erroneous values, but relevant samples, the rejection of which will lead to serious errors at the stage of energy management system implementation. Therefore, decisions must be made based on deep understanding of the nature of the outliers and the problem under consideration. Well, the last of the considered operations is missing values processing. Well, missing values processing deal with various mathematical approaches which can be like keeping the static value previously measured for a very specific process under consideration, or like putting some mean standard value which is typically observed for this specific object under consideration. So whatever, there are many approaches, but the option of missing values processing is is of great importance for energy management systems design. Well, what I just want to say that data processing is a stage of crucial importance, and we need to address the system before implementing energy management systems, and we have to be very careful in order to keep the relevant data and reject the erroneous data in a proper way. Well, now let's talk about missing data. If there is a lot of data, but there are few missing values, you can simply discard some objects with missing values and or discard a gapped feature, remove columns. It's up to you. But if it is not the case, or for example, the very specific measurement is of great importance, then you need to fill in the gaps. There are several approaches how to do this. To choose the most appropriate value to fill each gap. So you can choose mean, median, or mode. Another simple approach is to treat gaps as a special type of value. More sophisticated but potentially more efficient are some unsupervised missing value recovery algorithms, such as detecting the most similar objects and using their values. And finally, we have the option of doing nothing with the gaps just by using algorithms that are initially designed to allow gaps in the initial data. But anyway, missing data issue is of great importance for EMS systems as well. Well, now let's move on to data transformation issues. First of all, data can be divided into numerical and categorical types. For numerical data, a change in their dimension, distribution, or more complex types of transformations can increase the importance of the parameter for the energy management system. For categorical data, the task is usually to represent it numerically. For example, a text category can be turned into a numerical identifier, like identifying the weather type, sunny, cloudy, partly cloudy, or identifying the operation state of the photovoltaic power plant, like grid connected, islanded, whatever. Feature selection falls into three general classes: intrinsic methods, filter methods, and wrapper methods. Actually, feature selection is of great importance because at this stage you identify the relevant demanded data which will be used by your energy management system to produce the desired output. Intrinsic methods have feature selection naturally incorporated with the modeling process. Various filter and wrapper methods work to marry feature selection approaches with modeling techniques. The advantage of implicit feature selection methods is that they are relatively fast, since the selection process is embedded within the model fitting process. Filter methods conduct an initial supervised analysis of the predictors to determine which are important and then only to provide these to the model. And wrapper methods use iterative search procedures that repeatedly supply predictor subsets to model and then use the selection on the next subset to evaluate. Well, actually, the data exploration and feature selection based on their importance is of crucial value for the energy management systems implementation because you define what the features are used for and what features are important in order to get the desired result of your subtasks which you are attempting to solve within the framework of monitoring, control, whatever you deal with for a specific object under consideration. Now we move on to data visualization. Actually, visualization is an important tool for data processing when designing energy management systems as well, because it allows to present complex information in a visual form that can be perceived and interpreted by a specialist, maybe a dispatch control staff. For example, looking at such a very small table, giving at the left side of the slide, we cannot understand how the objects of the two classes are distributed. But visualization allows us to capture the whole picture, yep, and get the classification based on the concepts introduced in the plot. Well, there are more than a dozen types of graphs for data visualization. For example, box and viscous plot enables to quickly get an idea of the data distribution only with the most important characteristics: the scatter, the presence of potential outliers, quartiles, median, and mean. Anyway, from the first sight, it may look rather complicated, but understanding of this graph will give you a powerful tool for data analysis and even a powerful tool for data filtration when you implement it as a sort of the barrier, yeah, before the data enters the storage capacities of the energy management system that you implement. Okay, so there are more than a dozen types for data visualization. Yeah, so as I have already mentioned, and this very specific example illustrates the box and whiskers diagram, which is implemented for analysis of the weather conditions. So this can also help us to understand the background behind these measurements of weather data, which can potentially improve the performance of the energy management system of PV power plant energy production forecasting, for instance. Well, now let's consider energy management system designed for a PV power plant. And this slide presents us a single line diagram of forecasting subsystem of photovoltaic EMS. And this task is of crucial importance because without forecasting the photovoltaic generation, you will never be able to ensure reliable balance of the energy generation and energy consumption in the power system, as far as solar energy is highly stochastic. Before taking the problem of photovoltaic power plants forecasting, first of all, we identify the important values within the framework of the input data set. It's like adjacent power network parameters, like switched on and switched off power transmission lines, because they may impose some additional constraints from the point of view of photovoltaic power plants output in terms of providing the generation of the rated capacity of PV power plant if we have sunny weather, for instance. Then we have weather data, which is of crucial importance for our task as well, because clouds, fog, or just like some sort of storms, they impact the generation capacity of the photovoltaic power plant greatly. We have to keep in mind solar power plant configuration because even some service and maintenance actions like taking the inverter for maintenance and service provides disconnection of a part of PV panels, and that means we are no longer able to produce the rated capacity of the PV power plant. So we have to take this into account as well. Of course, there is some geography data, which gives us the more detailed understanding of the PV location. Weather monitoring system data, which includes wind speed meter, solar irradiation meter, like humidity and temperature as well. And finally, power equipment passport data, because actually power equipment passport data, including the passports of photovoltaic panels, they gives us the general understanding of what is the what is the operation state of each specific panel. Actually, this is needed to calculate the total output capacity of photovoltaic power plant. All this input data corresponds to different data sources because adjacent power network parameters are extracted from the dispatch control center. For example, it's the issue of Scada interconnection. So we get this data from the outer source. Weather data is extracted from the internet based on some arrangements and agreements with the weather data providers. Solar power plant configuration is built based on the discrete signals of the primary equipment installed at PV site. Geographical data can be extracted from some GIS system. Weather monitoring system data is collected from the local meteorological station. And finally, we have power equipment passport data, which are quite static because we can store this data before implementing energy management systems. So it's just like the very basic data already stored in the specific data storage facilities. Next, we have this data preprocessing subsystem, which gives us the opportunity to make like data transformations because, for example, for weather data, We may have some categorical features like weather type, sunny, cloudy, partly cloudy, whatever. So we are expected to introduce some categories to this data. We may convert some like geographical data. It's not just the picture, but maybe the coordinates. So whatever, we make all the necessary actions with cleaning, filtration, removing the outliers, comparing with the bottom and with the top, yes, constraints of the data that we collect from the outer data sources. So we perform all the required actions, yes, in order to get the best possible composition of the data for our forecasting system, which is implemented as a subtask of the EMS. At the next stage, we get this task of solar power plant output forecasting and weather data and solar irradiation forecasting, which will give us the opportunity to make a prediction given a time horizon, yes, of PV power plant forecasting system implementation. Well, finally, we get this forecast, and what is really important, so we implement it in a form of a user-friendly interface because it's not a great deal to provide all this data to the engineering stuff, yeah, and make the forecast of the photovoltaic power plant. Of course, we have to think about the user-friendly interface, which will be useful to solve the tasks associated with photovoltaic power plant separation, like bidding at the wholesale energy market, like forecasting the operation modes for dispatch control system operator, so whatever. We have to think about adequate human-machine interface. These slides illustrates the example of really existing software tool implemented for energy management system at photovoltaic power plant. So at the upper side, we have these values of the actual generation forecast, generation forecasting error. We have the actual value of solar irradiation, forecast of actual of solar irradiation, and solar irradiation forecasting error. So in green, actually, we have here the forecast. In blue, these are the actual values provided for this very specific power plant. At the lower side, there is a graph illustrating us many useful, yes, operational parameters like some cloudiness, which actually illustrates the impact of the external weather conditions on the photovoltaic power plant's operation. So this is the window which is used by the engineering staff at the photovoltaic power plant to solve the problem of preparing the bids, yes, for the wholesale energy market, and to solve the problem of power of photovoltaic power plant planning, yeah, for day ahead perspective, because based on these forecasts, service and maintenance are planned as well. Well, now let's talk about data flow within the framework of the photovoltaic power plant. Let's consider the different data sources associated with the PV panel. Well, for a PV panel, we have these temperature sensors, which provide information, which provide data on the temperature of the surface of the solar panel, which actually has a great impact on photovoltaic panel production efficiency. Within the framework of the PV power plant, we have this horizontally installed irradiance pyranometer and solar irradiance pyranometer, which is tilted in the same plane like the PV panel. Well, we have the inverters, which provide us with the corresponding data of the electrical currents on DC and AC sides of the PV power plant as well. Moreover, at the photovoltaic power plant, we have the weather stations, which provides us with the relevant data of the current wind speed, current humidity, temperature, whatever. So it means that we have many data sources within the framework of the local power plant, which may be useful for us to tune, adjust, and even design the energy management system. Moreover, within the framework of consideration of external data sources, so we implement external weather forecasts, which may be of great importance for us when designing and implementing photovoltaic power plants forecasting systems. Being more specific about the characteristics of external data sources, we have to select, combine, yeah, and compare with each other different data sources. And this slide gives you an example of a comparison of different weather providers' data from the point of view of applying this data to photovoltaic power plants forecasting problem. So we take into account the existing of actual data retrospective availability, so we analyze data characteristics. It means what kind of models are implemented to get these weather forecasts for day ahead perspective. And even these numerical weather prediction models may have different characteristics as well, like different resolution, different models of taking into account the atmosphere of the Earth, whatever. So moreover, it's of great deal to take into account the distance of the photovoltaic power plant from the nearest meteorological station. So this will give us at least the general understanding whether we can rely on the data that we acquire from external weather providers or we cannot do it at all. Of course, we have to consider the organizational issues like using the forecasting retrospective, because when you create the model, you may use actual data, but when you implement the model, you have to use forecasting data, which may be a little bit different. For this reason, analysis of forecasting retrospective is of great importance. And for both of the weather providers, the retrospective of the forecasts is just a contract-based data supply option. So we have to analyze specific features of cloudiness forecasts and specific features of, for example, cloudiness actual values accuracy. And well, what is actually the value when we represent the cloudiness, like it's given in percentage or it's given in linguistic characteristics? It depends on the data source that we select for each specific problem under consideration. When dealing with data analysis of the photovoltaic power plant, I recommend you to make the step-by-step, day-by-day analysis of the data associated with the energy production of the PV power plant and the value of clouds, because you will really see that the practically the same value of clouds, like it's presented here in the right side of the slide, it's 90% clouds and 100% clouds, result in dramatic difference in energy production or in solar irradiation fixed by the horizontally installed pyranometer. And we may have errors associated with like data contradictions, because sometimes the greater cloudiness may correspond to the greater irradiation, yeah, and the lower cloudiness may correspond to the lower irradiation, which is actually impossible from physical point of view. And for this reason, data analysis, data preprocessing, selecting relevant data sources is of crucial importance for energy management systems and for solving each specific task within the framework of implementing this energy management system for practice. Well, just saying a few words about data analysis and the importance of data analysis for solving energy management subtasks. For example, forecasting of photovoltaic power plants energy production. This slide gives us the results of the comparison of PV power plant energy production given various cloudiness conditions for different types of the day, like morning, evening, noon, before and afternoon as well. And for the right plots in vertical axis, we have the transparency index, which actually illustrates the share of actual energy production compared to the maximum possible energy production for each specific hour. In horizontal axis, you see different values of cloudiness. Well, um, let's try to analyze these plots, yes, and get the general idea of the necessity of making this data analysis. For instance, for zero cloudiness conditions, we have the dispersion, yes, of the transparency index ranged from 0 to 1. So it's just like it's not more accurate than random guessing. The same goes actually for zero point 0.5 cloudiness. So we have the transparency index ranging from 0 and up to 0.85. So what I'm just trying to say that similar and like equal weather conditions from the point of view of the cloudiness, they result in great range of possible um, transparency indexes for for this specific power plant under consideration. So this requires like very serious actions dealing with data preprocessing because we have to think about what feature in the data set we are looking, what data source we are looking as well, maybe some extra data on weather events, on weather conditions like precipitation as well, may introduce more effect and make the resulting forecasting model more accurate. Well, the example of one of the existing EMS systems for photovoltaic power plants prediction, actually we've taken part in designing, yes, of this system together with Subsystems, and the software is called EnergySphere, and it provides us with the needed output, yes, to make this for photovoltaic power plants predictions uh, in order to make the participation of the PV power plant in the power system operation and control more effective, and in order to prepare adequate market bids at the wholesale energy market. At the left lower table, you may see the accuracy characteristics of the system that we were able to get. Well, now we are smoothly coming to the lecture learning outcomes. And first of all, I would like to state that energy management systems, they are of crucial importance for automated control monitoring of power system facilities. And it is of crucial importance both for big power systems in general with great dispatch control centers and for small power system facilities, because at each level of hierarchy in the power system, you need to control different values and you need to provide efficient decision supporting tool for the engineering staff. Data flow in energy management systems is arranged from various internal and external sources. And what we have to do is to select the relevant sources and to think about data processing as well. Actually, the latter one is one of the crucial stages of EMS system design. And well, I would say that data issues combining data sources, pre-processing, visualization is some sort of a heart, yeah, of energy management system, and it should be treated in a proper way. User-friendly visualization in energy management systems ensures effective interaction with the user, and actually it is one of the great issues to be dealt with. And the same goes for your project case, because when you prepare your project case solution in terms of photovoltaic power plants forecasting, please be sure that the results that you are presenting are user friendly and they are like understandable from the point of view of the expert board, which is going to judge the level, the efficiency of your solution. Photovoltaic power plants require object-level energy management systems solving specific tasks like renewable energy forecasting, maintenance, service, market bidding, whatever. So it means that Each specific facility in the power system, even the power system in general, has its own tasks and objectives within the framework of energy management systems, which are of crucial importance to make the power supply efficient, qualitative, and secure. Thank you very much for your attention. It was Stanislav. Hope to see you next time. Bye bye.